All right, howdy everyone. Today I'm going to be demoing PA5, and I already did the demo, but I forgot to screen record. It's been a long night, but yeah, let's get into this. All right, so I'm going to be sharing my implementation for PA5, which is in this PA we're getting rid of these worker threads, which basically use the cwrite, cread, and this creates a little bit of a delay and kind of the threads have to wait on each other because only one thread can be accessing these two at one time. So a lot of efficiency is lost, and this is kind of what I'm talking about. cwrite, and you got to wait on that thread. Cread back, and this is the delay that we want to get rid of. Obviously, we have hundreds of threads in the last PA that was giving us some pretty good performance, but we weren't really worrying too much about the efficiency. In this PA, the implementation was to just send all these requests initially. So we basically make this epoll list, and we warm it up by gathering all these messages, sending them through, and then we send these initial requests over. We wait for any of the requests, the read requests to come back, and we handle them individually and then send them back out. So these are out of order responses, and there is no this perceived delay. Though we're only going to be waiting on using epoll wait for the whichever read request comes back from the server. And so this is a much more efficient implementation, and it's called like out of order arrival, and we're going to be using IO multiplexing with this epoll. Just basically choosing which one, and we're going to be needing to implement some like data structures to keep track of like our the mapping and the state of the message of the channel that we're looking at. So this is our event polling function. First, we do this epoll create, and we create this empty poll list. If that file descriptor is -1, then we say exit on error. Else, we just prime this list by let's see. Yeah, so we prime this list by popping a request buffer of size buffer, and then this thing that we pop, we typecast a message type pointer, and then based on whatever the message type is, like quit message, then we push the quit message to the request buffer. Else, in this case, we can begin our like implementation of the like the non-blocking or whatever it's called. The term for it. Yeah, decoupled. So this decoupled cwrite, we can write this buffer to the channel, but we have to gather the state of the channel. So this vector char buff to buff plus size. So yeah, our size is just simply the message. And so we save this message into the state of I, so we know what the state of this channel is, what we're sending to the server, and that's important information. Nsent is incremented. Basically, we send over one. We need to keep track of these two variables, nsent and nreceived, because this is crucial to our looping logic in these while loops that we're going to be using. We're just using one while loop, but it's crucial for that logic because we need to break out of that loop when we're done with this thread. And yeah, so here we have this file descriptor. It's get RFD, and then that can be shown here. in our histogram collection. So get RFD, and we just return the file descriptor, read file descriptor. And then FCNTL. So this will alter our file descriptor based on, we'll make it non-blocking. So the set flag non-blocking. And then we monitor this file descriptor. So if it's armed or unarmed, read or unread. And then we set this event.data.file descriptor to this file descriptor. So these are our lists. And then now we can map this file descriptor. We're linking this file descriptor of this current channel to the I in our for loop. So when we need to, when we're reading these requests in random order, we kind of have an idea of what our index will be just by accessing FD to index of the RFD of that specific channel that we're getting, because we cannot get the index just by getting request. It's quite difficult. So this is the implementation for that. So at this point in the code, we are done sending, and now we will wait using epoll, and yeah, we will wait until we receive a file descriptor of like a channel. And this here if statement, this is gonna be us breaking when we've received the quit receive flag, and our number of received and number of sent are the same. And yeah, epoll wait, this is the function that we'll be doing. So since we're doing the decoupling, we need to have this epoll wait right here. So we wait until we receive another message. So in this case, we wait for this list for any of these channels, number of channels. And so if none of them are, if we're still waiting, then we just do epoll wait. But else if like we have some file descriptors given to us, we will sort them in the order they came. So here we're going to do some decoding, some multiplexing. So we need to get our file descriptor back. So we do events of I dot data dot file descriptor. So now we can get our file descriptor of the channel, and then now we decode that using our map file descriptor to index. So file descriptor is our index, and we use our map, and we get our actual index for our channel. So now we can do cread wchans of our index. So now we see read and receive buffer. And then we can increment the received channels because we've received the channel now. Now we have to process this. So request equals state of that index. So we're giving the state of the channel. So we had to save that previously in our vector. Now we can pull that out and set it to our request vector of characters, and then we pull the data from that and typecast it to a message pointer. And then now here's our implementation for like if it's a data message or if it's also if it's a file message. For data message, we do create this response object, and that's just for the person. And then we push this to the response buffer. And then if it's a file message, we just do the implementation of our file message from PA4. So once that's done, we can actually send our, we can go ahead and do what we did right here, sending the message. We can go ahead and do it again. So like here, when we send this right out, it's like sitting idle. We got it back, but we can use that guy too. So if we haven't received a quit message, then we're gonna pop the request buffer again, just like we did back up here, right here. I'm gonna do that again, and then in this case, we know we don't have a quit message because we used the if statement. We don't have to worry about this, and then we can do cwrite again. Well, we're just, this is just like our implementation is efficient. So yeah, cwrite, and then we save the state of that channel again. Make sure to pull the data from the buffer. It's not a quit message. Then yeah, we do a cwrite. So yeah, no, we have to use the if statement still. But this if statement will just raise our flag for our next loop so we can break out of it. But yeah, else wchans of index, and that index is still being used because I mean this is the channel that we received at random. We need to be using that specific channel again. Not all channels are back yet. These are just coming in at random. So we're sending them back out again. All hands on deck. Yeah, cwrite buffer. Save the state of that. Then we increment end sent again. Yeah, that is how it should be. So yeah, let me talk a little bit about these end sent and end received variables. So if it's not quit received, then we go ahead and do this. But if it is, then we go up here and then we check again that if it's like, so we got to go through this while loop, and then it's a while true. So here we have our break statement. If quit received and end received equals end sent, then we can break, because that means that all respective channels have been dealt with, and they're both the same amount. You know, we don't have some people stuck over here coming back or whatnot. They're both on the same opposite sides, so we are done. And yeah, that would be the end of our threads functionality. And remember, this thread is just one single thread, and these are all of our parameters. Much more parameters, but same idea. We don't have to make any for loops, just one thread. We still have our 15 not p patient threads, h histograms, h histogram threads, actually p histograms, and yeah. So based on if it's a file transfer or a message or data transfer, we handle that. Then we have to join our event. What's it called again? Event polling function. After our patients are joined, and then we push this response buffer to the histogram. No, yeah, we push the response to the response buffer, and then we join the histograms. And then here's our file thread. Then we just do event polling thread, same parameters, and then file thread joined, request buffer push, and then join the event thread. Oh wow, my PC is very loud. Why is it running so hot? What in the... Oh yeah, I'm screen recording. I need to get a new case. All right. So, and then we have to deal with deallocating our memory, since we allocated some memory on the heap with our where is it? Yeah, so this, what is this? Um, oh yeah, okay. There it is. So yeah, we have to allocate W channels, which is a pointer of arrays, array pointer of FIFO request channel pointers. And yeah, we initialize all these W channels, and yeah, we have to deallocate them here in this for loop, and we delete the actual array. And then we also have to delete our histograms, but we can't really do it from here unless we made a pointer, or we could just make a member function in yeah, so in the histogram we made delete hist, and we just delete hist. This should be, and I think I accidentally pasted something and I have an error, but yeah, so that should be it with for implementation. Let me check any of the rubric steps. Yeah, we don't have global variables. We clean up FIFO files, and so yeah, we primed the channels, we removed the unnecessary locking, we made them unbounded. We maintained the vector for the state, and then we have proper termination. I can go ahead and now do some thread testing. So we can start at 100 channels. And let's look at our CPU usage. Okay, 100, out to 200. So the primary goal of this PA really wasn't to make it much faster. It was just to increase the efficiency, like I said before. So 4.4. And so let's compare this to the data of PA4 that I 4.3. So when I was testing this earlier, I was getting around the same time, but here I have like slightly more time. And yeah, so that just proves that in this case, we're really not focusing on the max performance. That we're honestly, on the other hand, just doing this more efficiently in the way it should be done. Because now that we're overcoming the obstacle of having this perceived delay right here. Although we're running like what 500 threads in that case, so it's going to be more intensive work, but this is the better implementation in my opinion. And then let's just go ahead and do 300. Yeah, so earlier when I was demoing this PA without using the screen record, my times were like, yeah, so right here, 300 took 2.3 seconds, and now it's taking 3.8, which is weird, but I do have proof that my implementation was working somewhat faster than PA4. Let's try file transfer, why not? File transfer. Ooh. Yeah, 15,000. Our output is, yep, all done, server terminated, no memory leaks. File transfer correct counts in the histogram. Our histograms are outputting the correct values. flag was 15,000 data points, 15 patients. So yeah, 15 patients, 15,000 data points for each. It's just weird that this timing is how it is. And yeah, our bounded buffer implementation is literally the same because we need to be using these same mutex locks in the same implementation, but in our implementation of the event polling function, we get rid of the cwrite, cread. Let me see if I can pull up the PA4 solution. This is a PA4 solution. And we go to worker thread, and yep, here's our like, this is the flaw, fatal flaw that we overcame. So all in all, great implementation. And yeah, that was my demo for this PA. Thank you guys for watching, and I appreciate you guys.